So today we're starting with the simplifying square roots. And when we simplify square roots, we use something called the product property. And basically it's saying if you have two numbers that are being multiplied by each other inside of a single radical, you can technically rewrite it as two numbers in separate radicals being multiplied by each other as well. All right, so we can use this property to simplify square roots. So like square root of 8, you could technically rewrite that as 2 root 2. And if you put both of them in your calculator, you would get the exact same number, 2.828. All right, and the reason it works is because square root of 8 can be broken down. So square root of 8 is the same thing as like 4 times 2 inside of a single radical, which then we could write as 4 times 2 in separate radicals. And the square root of 4 is just 2. So it simplifies all the way down to 2 root 2. All right, so rules of radical simplification. One of the rules is when we're done simplifying, we want no radicand. All right, that's going to be a number like square root of 7. All right, has a perfect square other than 1. That's one rule of radical simplification. We simplify and then we find out, hey, they don't have any perfect squares left except for 1. The other rule, no radicals in the denominator of a fraction. So if we ever have a radical in the denominator, we have to simplify it and get rid of that radical in the denominator. Okay, so here are a couple examples. What we can do is we can rewrite something. I always look for perfect squares when I'm doing these types of problems. So think about perfect squares. I mean like 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, 15 squared is 225, and it just keeps going on forever. We can keep scoring numbers. But when I'm breaking these down, I'm always trying to look for perfect square values like these right here. Those are the numbers you want to look for inside radicals, because once you get a number like that inside of a radical, you can square root that number and pull it outside of the radical, and it simplifies the radical a little bit. So for example, another way you could do these problems is you could just do what's called prime factorization. So let me show you this first problem. Problem 1, square root of 18. Right off the bat, I know that I can divide a 9 out of 18, and I'm going to be left with a 2. So 2 times 9 is 18. Okay, so square root of 9 times square root of 2. And then I know that the square root of 9 is 3. So this simplifies to 3 root 2. All right. The other way you could do it is you could do what's called prime factorization, which is you say, let's take 18, and I'm going to divide it by 2. I'm going to be left with a 9. 9 I can divide by 3, and I'm going to get another 3. And what that gives me is 2 times 3 times 3. And if you recognize, hey, I have 2 of the exact same number inside the radical, I can pull that number outside of the radical. And then I'm going to be left with the 3 root 2. Either way is perfectly fine to do it. Okay, so whatever method works better for you. Me personally, I like to look for the perfect square, and then I know I can pull that number out of the radical and square root it. Okay, that's the way I like to do it. All right, so second problem here, square root of 40, we could pull out a 2, and we'd be left with a 20. We could pull out another 2, and we'd be left with a 10. We could pull out another 2, and we'd be left with a 5. And that's down to prime factorization. So we end up getting 2 times 2 times 2 times 5. And then say any pairs that we have, we can pull out. Hey, I've got a pair of 2s there. I can pull those out. And I'm still left with a 2 times 5. Unfortunately, that's not going to simplify. So I just put it back together and say 2 root 10. That's my simplified expression here. Okay. When I get to something like problem 3, I say, okay, let's see here. We can pull we can't pull a 2 out of 85. Can't pull a 3 out of 85. Can't pull 4 out of it, but I can pull 5 out of it. I can get 5 times 17. 5 times 17 equals 85, but unfortunately 5 is not square rootable. 17 is a prime number, that's not square rootable. So this one simply cannot simplify. And that's possible to happen sometimes. Sometimes we already have the simplest radical. So square root of 85 is the simplest. All right. Now I have square root of 6 times square root of 21. Instead of multiplying these together, I'm just going to break them down individually. 6 is 3 times 2. 21, 3 times 7. Those are all the prime numbers. So now I've got 3 times 2 times 3 times 7. And look at that, I've got 2 3s hiding out in here. So I'm going to have 3 times square root of 2 times 7. So that is 3 root 14. That'd be as simple as that one's going to get. Once I see 2 3s, I can pull those out. That's one way we could do this method. Problem number 5, whenever we see a radical like this, we can technically rewrite that as square root of 4 divided by square root of 81. And we'll see that we have a radical in the denominator there. And we don't like radicals in denominators, but thankfully for this one, 4 is a perfect square. So square root of 4 is 2. 81 is a perfect square. That's 9. So this simplifies to 2/9. And then last one, problem 6, square root of 7/16. That's the square root of 7 over the square root of 16. Well, square root of 7 is not going to simplify, but square root of 16 is 4. And thankfully, we don't have a radical in the denominator. But those are 6 good examples right there. Now I want you guys to try the next 6. Try practicing on your own to simplify all of those radicals. Rewrite those expressions for us. All right, let's take a look at these 6 problems. So the first one, part A, you can break it down to 3 and 9. And this is kind of what I like to do, where I like to say, hey, that's square root of 3 times square root of 9. And then I see, hey, I know square root of 9 is just a 3, so I'm going to end up with a 3 root 3 there. But the other method that I've just been showing you on the practice is you would take the square root of 27, and you'd break it down to 3 and 9, and then the 9 breaks down to 3 and 3. So you get 3 times 3 times 3. And you could say, I got 2 3s inside the radical that need to drop out. So then I'm going to pull a 3 out, and I'd end up with 3 root 3. Either method you want to do is perfectly fine. part B, divide by 2, and you're going to end up with a 49. And I like that because now I've got, hey, look, a square root of 49 there. So I know square root of 49 is just going to be 7, so I get 7 root 2. All right. Part C, 10 times 15. This is where the other method might work a little better because I can break down 10 to 2 and 5. I can break down 15 to 3 and 5. And now if I write this together, I can say 5 times 5 times 3 times 2. And for part C, I can see I've got 2 5s inside the radical, so I can pull a 5 out. And I'm going to be left with 3 times 2, which is 6. So this becomes 5 root 6. Part D, 9 64ths. So it's square root of 9 over square root of 64. Square root of 9 happens to be 3. Square root of 64 is 8. So it's 3/8. Part E, square root of 15 over square root of 4. Well, square root of 4 is going to be 2. Square root of 15 can break down to 5 times 3. Unfortunately, that's not going to simplify, so this is going to be root 15 over 2. And then last one, part F, square root of 11 over square root of 25. 11's a prime number, so that's done. Square root of 25 is 5. So we would just simplify it like that. All right. So now, sometimes we're going to have a radical in the denominator, like all the examples we did so far. The radicals worked out in the denominator. Okay. But sometimes we will have to rationalize the denominator, which means we have to get rid of a radical in the denominator. And we're going to look at a couple different examples of how those could look. The first example, if we have a denominator that is like square root of b, all right, we're going to multiply the numerator and denominator by that square root of b. And the way that looks is, let's just say we have 3 over square root of b. We're multiplying, like I said, numerator and denominator by square root of b. Because when we're multiplying by the same number on numerator and denominator, square root of b divided by square root of b, what are we really multiplying by? Just the number 1. So we're not changing the value of the equation at all. So what happens, we get 3 square root of b over square root of b squared. And the square root of b squared is b. So we would just simplify to the letter b. And now we don't have a radical in the denominator anymore. That's kind of nice. Okay, so that's the first example that we could deal with. The other example we could deal with is we might have something like a plus the square root of b in the denominator, or a minus the square root of b in the denominator. And the way you get rid of an a plus the square root of b or an a minus square root of b is you multiply by the opposite sign. So you would just say a minus the square root of b, which is called the conjugate. And I'll show you an example of this in a second. We're going to multiply by the conjugate. Which is the opposite operation. All right. Let's take a look at our first example. I'll zoom out just a scotch. So our first example here is square root of 5 divided by square root of 2. And that we can rewrite as square root of 5 divided by square root of 2. And square root of 5 won't simplify, unfortunately. Square root of 2 also won't simplify, but we have a radical in the denominator. So I have to multiply both my numerator and denominator by square root of 2. And what's going to happen is on the numerator, I'm going to get square root of 5 times 2. On the denominator, I'm going to get square root of 2 times 2. And that becomes square root of 10 over square root of 4. And thankfully, square root of 4 is 2. So that simplifies for us, and that's it. Okay, that's the idea with these types of problems. Example 2, oops, I'll let you finish example 1, sorry. Example 2 is going to be one of those issues where we have we have to multiply by the conjugate because it's a 7 plus square root 2. So we're going to multiply the numerator and denominator by 7 minus square root 2. That's the conjugate of 7 plus square root 2. So the numerator, we'll just distribute here. 3 times 7 is 21. 3 times square root 2 is 3 square root 2. The denominator, I'm going to go to a factor box for this one, because this one's a tricky one. 7 times 7 is 49. 7 times positive root 2 is positive 7 root 2. 7 times negative root 2 is negative 7 root 2. And negative root 2 times positive root 2, that is negative root 4. And now I have 7 root 2 minus 7 root 2. That's a 0 root 2, which is just a 0. That's kind of nice. So what I've really come out with out of this box is I got a 49 and a negative root 4. So 49 minus square root of 4, which is 49 minus 2, which is 47. That's my denominator. And that's what I ended up with for this problem here. All right. So now there's 3 examples down here. I want you guys to try these 3 practice problems. Give them a shot. All right. And then if you finish those 3, you can actually even try the triangles as well. You're going to use radicals to provide exact answers in trigonometric problems. So we don't want, when you get down to these ones, exact answers. I don't want decimal answers. Exact means radicals, okay? So give those a try. Let's take a look at these last few problems here. So we're given angle theta, but it doesn't matter because this is a Pythagorean theorem problem. We're just looking for side x. So the hypotenuse is 15. So we can say 7 squared plus x squared equals 15 squared. End up getting 49, plus x squared equals 225. I'm going to subtract 49 from both sides. And what we've been doing so far, we'd get something like 176. We square root both sides. And we get square root of 176, plug that into our calculator. We get some weird decimal answer like 13.26. But what we want to do today is we want to simplify that 176 instead. We're going to do an exact answer. So I'm going to divide by 2. 88. Divide by 2 again. 44. Divide by 2. 22. Divide by 2. 11. So in reality, square root of 176 is really 2 times 2 times 2 times 2 times 11. And then I say, how many pairs of 2's do I have? Well, I have 1 pair of 2's right there. I've got another pair of 2's right there. So I can pull out 2 different 2's. And I'm left with a square root of 11. And that becomes 2 times 2 is 4, so this is 4 square root of 11. So in reality, side x is length 4 root 11. That's the exact answer. No decimals. The exact answer only. Okay? That's what I want to do with these types of problems. Example 2, the hypotenuse is 8. A little easier to see. So I get 36 plus x squared equals 64. Subtract 36 from both sides. I get x squared equals 28. I know I can pull out a 7 and a 4. And 4 breaks down to 2 and 2. So 2 times 2 times 7. That's our square root of 28. And because I have 2 times 2, I can pull out a 2. And I'm left with 2 root 7. So side x here is 2 square root 7 after all of that work. Okay. Problem 3 here. I start with the smaller triangle. I've got a side length 3 and a side length 4. So I can say 3 squared plus 4 squared equals x squared. That's going to be 9 plus 16 equals x squared. 25 equals x squared. So when I square root both sides, I actually just get 5 for x. That's kind of nice. On the other side, I have a different triangle that's also a right triangle, and I can find side length y. I know I have 3 squared plus y squared equals 7 squared. And I just work on each individual part. Oops, 9 plus y squared equals 49. Subtract 9 from both sides, y squared equals 40. I square root both sides, y equals the square root of 40. And I should be able to see square root of 40, that breaks down to like 4 times 10. This is one way I could do it. And the square root of 4 is 2. So I get 2 root 10. And that'd be my side length y. Alright, so I've got my x and my y for problem 3. Just break it down to 2 separate triangles, and you do Pythagorean theorem twice. And with the last problem here, problem 4, I'm going to get 10 squared plus x squared equals 12 squared. 10 squared is 100. 12 squared is 144. And I get x squared equals 44. When I square root both sides, x equals the square root of 44. And now I can break that down. I can divide by 2 and I get 22 left. Divide by 2 again, I get 11. So 2 times 2 times 11, that's the square root of 44. And I can see I have a couple 2's in there. So I can say this, write this as 2 square root of 11. That's our x. And then the very last triangle, this blue one here, I have side lengths 8 and 10. 8 squared plus 10 squared equals y squared. And I get 164 equals y squared. So y equals the square root of 164. And then I go ahead and break it down. So this last one I can say, all right, break down 164, and that's going to be 2 and 82, and then 2 and 41. 41's a prime number, so that's nice. It's just 2 times 2 times 41. And I end up with 2 square root 41 for this last problem. Sorry, I went through that kind of fast there at the end, but that's the idea with when we're doing triangles for these types of problems, what we want to do. Okay. Any questions on any of this stuff today? For your assignment tonight, you should be able to hopefully get it done fairly quickly. 12 problems total, simplifying radical expressions. Okay. So hopefully you can get that done fast. Tomorrow there's going to be a graded assignment. It's the Mod 4 graded assignment is posted on